Hello, good day, everyone. So, now we're going to study the three Newton's laws of motion. Okay, there are three Newton's laws of motion. There is what we call the first law, the law of inertia, the second law, the law of acceleration, and the third law is called as the law of interaction, or sometimes the law of action reaction. Let's start with the first law. Newton's first law. A body will not change its state of motion unless acted upon by an unbalanced force. What does that mean? But first, what is a balanced force? What is balance? If something is balanced, it's only either the object is at rest or moving with constant velocity. And in physics, if something is balanced, the net force is equal to zero. So let me write that. So let's say our object or our system is in the state of balance. Again, if you say that something is balanced, the net force is equal to zero. Summation of F equal to zero. The symbol here, sigma, the Greek letter sigma, it means summation. You're going to add all the forces. It means there are one, two, or more. Well, there will be at least two. So you're going to add two forces or more. So let's say you can have F1, force number 1 plus force number 2 plus force number 3 and so on. And then it should be equal to 0. It means they cancel out. If you're going to add them together, they cancel out. When you add force, it's a vector quantity, so you need to consider the direction. So it means, as for example, I am sitting, I am in a state of balance. I am at rest. I have a weight, the force is downward, and there's a support force on my body, that is the chair, the normal force. You know that from the previous lecture, right? Okay, so it says here that a body will not change its state of motion unless there is an external unbalanced force. So let's say I am sitting here. Pardon my drawing. So, okay, I'm sitting here. Okay, I will just stay here forever. I will not change my state of motion unless I pull myself up or someone pushed me. So my state of motion or my state is now I can accelerate like this, like that, or I lift myself up. Okay? You will stay there forever, sitting, unless someone pushed you or you pull yourself up. Okay? So that is at rest. But uh, a balanced state is also moving with constant velocity. So let's say you're riding a bike. How do I draw a bike? I'm not, something like that. You draw a bike and you pedal here. You're sitting here. You're holding this one. So if you're moving with constant velocity, so this is at rest, or moving with constant velocity, you are still in balanced state. So object in motion with constant velocity will move with constant velocity forever unless acted upon by an unbalanced force. So let's say I have a car, this car will move forever unless there's an unbalanced force. And what is that? It can be the brake or it can be the friction on the surface. It will not move forever because of friction or even worse, air resistance. So it opposes. Okay? So, but if there's no air resistance, there's no friction, it will move forever with constant velocity. Okay? So now let's talk about a concept. Like every one of us has mass. Okay? Mass is actually a measure of inertia. Now, what is inertia? Here I have here the definition of inertia. Inertia is the tendency of a body to resist the change of state of motion. So that's your mass. If you have more mass, it means you have more tendency to resist motion. I just want to be here. I will not move. I have that tendency. But if I have smaller inertia, then I have a lower tendency to resist motion. So, for example, this one has a lower inertia. It has a low tendency to resist motion. It will just move, move, move. But if I have a higher mass paper object, it will tend to resist more motion as compared to this. As you can see, it just moves easier. So this is lower mass, lower inertia, higher mass, higher inertia. So that's your inertia. And of course, the unit for inertia and mass is what? As a unit, kilogram. So basically, the mass is your resistance to change the state of your motion, resistance to acceleration. Now, if you're studying Newton's law, some reminder, these are only valid if we consider an inertial reference frame. What is an inertial reference frame? It is a reference for you to say that you are moving. Okay? Inertial reference. How do you say that I am moving? With reference to the wall, which is at rest, or the ground, which is at rest. That's an inertial reference frame. Okay, but what if it's there's an earthquake? It might be that I'm stationary, but the walls are moving. So it seems that my reference now is accelerating or moving. So it's not valid. Newton's laws are not valid in those cases. We know for a fact, like even if we're at rest, let's say you're standing here, or there's a car here, you're standing in planet Earth. We are at rest. We consider this as inertial reference frame, at rest. But we know for a fact that Earth is rotating. So we're also part of that rotation. So we are not actually at rest. We are moving in a way, constant speed. Okay? But we know for a fact that the Earth is orbiting or revolving around the sun. So we are rotating, we are revolving, and the whole solar system is revolving around the Milky Way galaxy. So nothing is at rest, really, right? But to study Newton's law, you have to assume something is at rest or something is moving with constant velocity. That is your reference. That is your inertial reference frame. So perhaps sometimes, sorry about that. Sometimes, you know, when you're riding a car, and then even if you're moving with fast speed, but if your velocity is constant, it seems at rest, right? It seems like, for example, if you see a person on the other side of the car, the world seems to stop. Both of you are not moving because both of you are moving constant velocity. But if you're from the outside, the velocity is actually really fast. Okay? If this starts to accelerate, then you don't have reference that, oh, I'm moving this or that. Perhaps you can experience this when you're waiting for the bus. Then there's another bus on the other side. The bus is moving, but you think, oh, we're moving already. Okay? So what is your reference? You cannot use accelerating bus as your reference. You thought you are moving, but it's actually the other bus who are moving. So again, Newton's laws is valid only if your reference frames are not moving or moving with constant velocity. Okay? So now, let's proceed to, let's have an example here. Okay, let's have another example of inertia, where you can observe inertia. Let me stop sharing. So perhaps you've noticed sometimes that, let's say you're sitting on a car, and then the car is at rest, and then the car starts to accelerate. Again, you have inertia. You have the tendency to resist motion. Your body just wants to be at rest. But the car is moving already, so your tendency is to something. You just want to be at rest there. Okay, you resist the change of motion. But let's say the car is now moving with constant velocity, and then suddenly it brakes. You just want to keep on moving. But the car stops already, so your tendency is to move like that. But the car is at rest already, or slowing down. Okay, so that is because you have inertia. Let's have another example. Our planet. Okay, so this is your planet Earth. If there's nothing, no sun, no everything, our planet will just tend to move in a straight line. It will tend to move in a straight line. Okay, it will just move there forever. But because of the gravity of the sun, of course, we are attracted towards the center of the sun. There's the force of gravity of the sun. So we are not going to move directly towards the sun. No, but somewhere it's a vector. So there's the force of gravity and original direction wherever we are going. So in effect, this will be the net force. So this is the net force. Okay, later on it becomes a constant speed, or at some part our planet will accelerate a bit. That's why it's orbital. Okay, and so it will be like this forever, right? Or at some point we might get closer to the sun. Okay, we have inertia. Now, as you can see, the moon is also attracted towards the center of the Earth. But of course, the moon has its own direction. So in a way, it will just orbit around the Earth, around Earth. Okay, so what will make our planet change its state of motion from orbiting around the sun? Perhaps an asteroid, or perhaps, I don't know, perhaps a comet. If a comet hits us, then we will change our state of motion. So let's say this is your comet. Okay, so that's the time that our state of motion will change if you have a comet. Okay, so now let's define this summation of F. If the net force is 0, either the object is at rest or moving at constant velocity, no acceleration. The forces, there can be a lot of forces, but they will just cancel out. Let's say the car is at rest. Oops. Car at rest. So what are the forces here? Of course, everything has mass. This has a weight. Okay, it has a weight, but there must be something that balances the weight, and that is the force applied by the ground. Okay, so you also have this force. We call that the normal force, or Fn. So they cancel out each other. So the car doesn't move up and down. The force are balanced, right? So now let's say the car is moving with a constant velocity. So let's say you have the force applied by the engine. Of course, you have the ground. And of course, there must be something that opposes for it to have a constant velocity. Constant. Okay? So there must be something. What is that? It can be the air resistance or the friction. So let's neglect air resistance for now. So there must be something that opposes so that it will have a balanced force, and that is a friction. So here you have the force by the engine, and here you have the force. We use a symbol small f for friction. Okay, so the summation of the forces here is equal to normal force, which is positive upward, minus the weight, negative downward, and then they will just cancel out, equal to 0. So in this case, normal force is equal to the weight. It's in a state of balance. And here, summation of all the forces, you have to the right, the force applied by the engine on the car and everything, the passengers as well inside. And to the left, you have the friction. And you can also have air resistance. So force of air resistance, I'll just call it FAR. So it's to the left as well, opposing the force of the engine. So minus friction minus force of air resistance equal to 0. Okay? So in a way, the force to the right is equal to the force to the left. So you can also have this equation there. Force applied by the engine is equal to friction plus force of air resistance. Okay, so in most cases in our sample problems, usually we state that, okay, air resistance neglect. So perhaps only these two, which is simpler to solve. Okay? Now, let's talk about Newton's second law. You can read this with me aloud. Newton's second law. An unbalanced force acting on a body will accelerate it. An unbalanced force acting on a body will accelerate. Okay, so I have here two ball pens. One is heavier than the other. This is plastic, and this is metal ball pen. The black one is metal. Okay? It will just stay there forever unless I apply an unbalanced force. So the unbalanced force will cause the metal ball pen to accelerate. Okay? But wait, which one will accelerate faster? The plastic ball pen or the metal ball pen? I will apply the same amount of force. Oops. So as you can see, the smaller mass will accelerate faster or will have higher acceleration. So you can see there that mass is inversely proportional to acceleration. While force is, of course, the higher the force that you apply, the faster it will accelerate. Okay, let me share my notes again. Okay, so this is now your object and you apply a force, F, and the acceleration depends on the force and of course, the mass of your object. But how is it related? Okay, how do you think it's related? Is it inversely proportional? Is it directly proportional? What do you think? Okay, so the unbalanced force will cause the object to accelerate. Common sense, if you apply a force, the object will accelerate. The higher the force, the higher the acceleration. So basically, it's directly proportional. So it's directly proportional to the F. So this is your directly proportional symbol. Okay? Common sense. But how about mass? How is it related? The smaller the mass, higher acceleration. The higher the mass, slower the acceleration. So they are inversely proportional. Okay? So there's no other factors affecting the acceleration. Okay? It's just the force and the mass. So that's why we have this equation. Acceleration equals F over M. I don't know. You can easily memorize this. Father over mother equals, I don't know, anak. I don't know. Makes sense, right? Or you can manipulate the equation. F equals MA. Okay, so this is the equation for the force, relating force, acceleration, and mass. So let me box that one. It's very important. And of course, what's the unit for acceleration? The unit for acceleration is meter per second squared. The unit for force is Newton. Or you have mass and meter per second squared. You have kilogram meter per second squared. So these are your SI unit for force. Okay? Now, take note that acceleration is also a vector similar to force. And usually you have at least two forces. Or yeah, you can have more forces, not only one. So usually you have a net force, not only one force. So you can also write this as summation of F equals MA. And these are vector quantities. So let's say this is your coordinates and this is your force. Okay, that is your force. Now that force has y component and x component. So it's a vector quantity. I'm writing here, same as with acceleration. Acceleration is also a vector. So it has y component and it has x component. So perhaps you can also write the equation. This has fx, fy, and this as fy, fx. So you might have two sets of equations later on when you're solving problems. So you can have perhaps summation of f or fx equals mass times acceleration along the x-axis, x component. Now mass is a scalar quantity, so we don't need to bother about the x and y component of mass. It's just a scalar quantity. And fy equals mass times acceleration along the y. Okay? So I think one example could be when of acceleration. The second law is when you, let's say you have wet hands and then there's water droplets on it, it will not accelerate until you apply an unbalanced force. When you do this, you cause the water droplets on your hand to accelerate, okay? And of course, the acceleration is dependent on the force that you apply and the mass of the water. The more water, it's harder to accelerate. The small droplets, they will easily accelerate. Okay, the next Newton's law is also a common sense law. It is the law of action-reaction, or the law of interaction. For every action, there is an equal and opposite reaction force. If you apply a force on a body, the body will apply the same amount of force, but opposite in direction. I will apply force to the right, this one will apply force to the left. Action-reaction. So you can write that as if body A applies a force on body B, then body B will apply a force on body A, but opposite direction, negative to that of force A on B. So if you push a wall, the wall will push you back. Does it make sense? Let me see. I will push a wall. It seems it's not pushing me. I'm just supporting it. I will push it farther. I will push it more. The wall pushed me back. Makes sense, right? So the more you apply force, the higher the reaction force. Equal in magnitude to the force that you apply, but opposite in direction. So perhaps if you hit a ball, see, the ball hit me back in a way. Oh, but if you hit a stone, you kick a stone, boom, the stone will kick you back. It hurts. Okay, makes sense now? So that's action-reaction. So here you have FA on B equals FB on A. So let's say you have a wall. Oops. You apply a force on the wall, A on B. That's equal to the force applied by the wall, B on A on you, but negative to the left, negative direction. Another example would be rocket. Rocket applies the simple concept of action-reaction. The rocket pushes the air downward, and then the air will push it upward. It's action-reaction. It's like the engine produces an explosion, and an explosion of this fire here will cause the rocket to fly. And of course, the air will be pushed downwards. It's also action-reaction. And also, if you kick a ball, this is my foot. If you kick a ball, the ball will kick you back, something like that. Okay, so those are some of the application of action-reaction. Now, this is I've taken this from the movie Gravity. I don't know if you've watched it. Like accidentally, your cable is cut, and you cut from the spaceship. And just a thought, let's say there's no air resistance, there's no friction, just you are in space, and then you have no cables, and you accidentally push the spaceship. Okay, it means the spaceship will push you back. So the spaceship will move to that direction, but the spaceship, since it will apply the same amount of force, will also going to move in the opposite direction. So let's say you apply a force by the astronaut on spaceship, then the spaceship will apply the same amount of force on the astronaut, but this time opposite direction. Okay? So your mass, the mass of the astronaut, is smaller as compared to the mass of the spaceship. So this is bigger. Okay? So it means smaller mass, acceleration higher. The acceleration of the astronaut is faster or higher than the acceleration of your spaceship. Makes sense? So you will move faster, but the spaceship will just move slower. So what will happen to you? If you are now moving there, going in that direction, you will move forever. You will die because of the harsh environment of outer space. Okay? So I think we can end this session with trying to answer this sample question. So how does a person get a whiplash? And how do you avoid neck injuries caused by whiplash? So whiplash happens if the car is moving and then suddenly it brakes, so you might your head will move forward. Okay, so of course the best way is to use the seat belt, but sometimes if you're using seat belt, then you might have a neck injury because of whiplash. So better way to avoid it is you drive smoothly, brake smoothly. Don't you might get whiplash like that because even if you are this is one body. As you can see, in a way, you can consider your head as a separate part, and the body is a separate part. Your head will have lower inertia, so it will accelerate, freely as compared to the body, which is bigger, higher mass, so higher inertia. So they will not move, accelerate, or resist same. So that can be a danger for you to get injury. You drive fast and brake fast and accelerate fast. So here there's another question. Is it possible for an object to be in equilibrium if there's only one force acting on it? Okay, so perhaps you can answer in the comment. I will comment as well, and I will tell you the answer later on. So that's it for this session on Newton's laws. We have three Newton's laws. The first law, the law of inertia. Second law, the law of acceleration. And the third law, the law of action-reaction or the law of interaction. Okay, see you next time for the next topic on physics. Bye-bye. Choose.